previous lesson, we described considerations for the host interface SeminRT application. By the end of this module, you'll be able to describe various types and purposes of diagrams to document your system. In Lesson 2, we'll talk about documenting your design by creation of a variety of diagrams. Talk about an overview of the different diagrams that you may use. We'll talk about creating a communication diagram in particular. Go through a selection of common compact RIO diagrams to show you what a completed system diagram is going to look like, and also talk about some additional documentation that may help you in designing your system. So first, let's talk about an overview of diagrams in general. Why should we bother creating a diagram for our system? Hopefully you laugh when I ask that, because they're one of the best ways to help us define the software components in the system, and also to provide documentation of the system as it goes forward. For myself, I'm a very visual person. That's why I like LabVIEW. I get to see what my code is doing. Having a diagram available to me to quickly learn what a piece of code is supposed to do is very helpful. When I'm designing my own systems, it's also a great way for me to think through what I want to build before I get into the code portion of it. It's much faster for me to diagram something, change my mind, scratch it out, try something else, and see how those pieces fit together, than if I was to actually implement everything in code, start running and realize, oops, I made a mistake. Much easier to clear something off a whiteboard or to delete something from a computer diagram. Also, this is a great artifact to use to document your system for the next person who's going to own it, or to the customer to whom you're delivering the system. In terms of communicating with customers, I find that they don't really want to see my LabVIEW code. They want to see a high-level diagram of what it is they paid for. They want to see how it talks to each other and what the different moving parts in the system are. For that, diagrams are invaluable because they provide a common language for us to speak. And since my role at NI is working with support, having a system diagram available to help people help you is always a great thing. Obviously, there's lots of types of diagrams. You could go all day and talk about the various types of diagrams that are out there. You have a communication diagram, a state diagram, a class diagram, a module hierarchy diagram, a use case diagram. Those diagrams with the stick figures and the lines, I don't really know what all of them are. I don't really care. Because I find that the ones that are most useful for my day-to-day work are going to be a physical, communication, and a state diagram. For what I need to do, these diagrams convey the information necessary. In your application, for example, if you're using a object-oriented based approach, you're probably going to want some additional types of diagramming. In those cases, I highly recommend taking the time to learn the UML diagrams. They will provide you with that common language which you can use to communicate with other object-oriented developers and your customers as well, if they're familiar with that language. It can be a very powerful tool to level that playing field. For this course, we'll just focus on physical communication and state. Just know that there's a lot of others available to you. To start, we're going to work with the communication diagram. Communication diagram is going to focus on displaying the different communication paths between the processes within your system. Now, if you like, this is going to be a diagram that shows the different targets, the different loops, and the connections between those loops. And as you might imagine, that'll map very well to your LabVIEW code, which on a LabVIEW diagram is going to look very similar. Loops connected by wires showing the communication paths between them. And I find that it's very useful for medium to large applications. If your application is a very simple thing that just reads data from a thermocouple and puts it to an indicator on the screen, you probably don't need to spend the time to make a diagram. For larger applications, as they scale bigger and bigger, these diagrams will help you keep track of what your system is doing, what's talking to what, and to keep your system organized. It's going to be a very good habit to get into. I find it's also very useful for applications that have multiple targets. So a real-time system, an FPGA, a desktop PC, perhaps multiple desktop PCs, a data storage server sitting off on your network. Any of these different pieces can be represented on these communication diagrams. In addition, you can also incorporate some components of physical and state diagram information within the communication diagram. And that way you can kind of consolidate that information in an easy to digest format. So now you can describe various types and purposes of diagrams. Coming up next, we're going to create a data communication diagram. In the previous section, we described various types and purposes of diagrams. By the end of this module, you'll be able to create your own data communication diagram. So the concept of a diagram hopefully makes sense. We want to make sure that we document our system and think through the design before we get started on the implementation phase. But how do we actually create one of these communication diagrams? The easiest way to do it is to first start with a physical diagram of your system. By this point, you should have chosen what hardware you're going to use to implement your system. In our case, we'll use a single human-machine interface computer, an HMI, and a single compact RIO system connected via Ethernet connection. So this will be an example of the physical diagram of your system. This is what you would see on your benchtop: a computer on the left, a compact RIO on the right, and an Ethernet link between them. Next, we're going to change the representation of the different hardware components from just a picture of a computer and a compact RIO to a little bit more logical representation. We're going to diagram the programmable hardware components. So on the left side, you have the HMI, the human-machine interface computer. On the right side, you have a compact RIO target, which contains a RT controller and an FPGA. If you notice, these are going to be represented as separate blocks within the compact RIO itself. Once we have the programmable targets defined, we're then going to diagram the top level VI for each target. So as you can see on the left side, within the HMI, we now have the HMI main.vi. HMI main is going to communicate via Ethernet to RT main, which runs on the compact RIO controller. RT main is then going to communicate via a communication path, be it registers or DMA, whatever we chose for the application, to FPGA main, which runs on the FPGA. The idea of this is so that we know which pieces of the system are talking to which other pieces, and where they're located in terms of the programming target. Next, we'll go one level deeper. So we have the HMI main VI, the RT main VI, and the FPGA main VI. That's that level. Then within each of those VIs, we've listed out the different processes that we're going to implement. So process 1 on HMI main is going to talk to process 1 on RT main. Process N on the HMI might talk to process N on the RT. The idea here is that these are going to be the different linkages that we'll need to implement in code. As you develop this process further and put more detail into the names of the processes and the communication links, you'll start to get a very good idea of what you need to program in your system. As you go through this process, you'll find that your code becomes much more efficient if you do the diagramming first. Because here it's very easy to determine, I need to have a different link here, or maybe I could combine these two different pieces into one so that I don't have 5 separate communication links. Maybe I can have a communication proxy process that handles all the communication over the network and routes communication internally as needed. The way I usually start is just by brainstorming. I don't like to do a lot of work and have that work go to waste. I usually change my mind a lot at the initial stages of a project, so I'll use the lowest effort method possible. I'll just draw it by hand. I'll just grab a whiteboard, grab a marker, and start scribbling. And as you can see in the picture we have here, sometimes that scribbling is a little bit messy, sometimes it's hard to follow, but it's a very good starting point, very low effort. It only takes a minute or two to start drawing these things out. Once I've drawn something out, once I've stopped continuously erasing and redrawing and coming up with different ways to organize it, at that point, once it's fairly stable, you should translate it into some vector-based drawing program so that you can maintain and share that documentation. Obviously, if I was to take this picture of a whiteboard and email it to my colleagues, they'd be coming to my desk pretty quickly asking me what the heck I was designing. If I put it into a more digestible, cleaner format, it's going to be a lot easier for them to understand what it is I'm trying to accomplish. So in terms of which vector-based drawing program to use, Well, that's really your choice, and much of it comes down to what your organizational structure looks like, what processes you normally follow in your workflow, and of course, which software you actually have licenses for. So many of the programs out there will give you specific support for drawing flowcharts and sharing data. This is a very incomplete list, of course, but there's a lot of software out there that you can grab. I should note that the G# Star UML plugin is available. Star UML is a UML diagramming tool for which one of our alliance partners has this plugin that you can use to translate between your UML diagram and LabVIEW code and vice versa. The one that we're going to use for this course is the YED graph editor, and this is available on the internet. It's a free download, and we're going to be using that throughout this class. In the previous section, we created a data communication diagram. By the end of this module, you'll be able to describe how to create your own data communication diagram using an example diagram application called YED. In this demonstration, I'll show you the basics of navigating through the YED graph editor environment to create a data communication diagram. The diagram is going to consist of a HMI PC, a compact RIO target containing both a real-time controller and an FPGA target. I'll show you how to create a simple data communication diagram with communication linkages between all these different components. To obtain the YED graph editor software, take a look in your demonstrations folder that got installed under C, Exercises, LabVIEW Real-Time 2, Demonstrations, or wherever you chose to install the files. You should find a YED graph editor download website text file, which contains the location to download the software. The software is a free download, and once you do that, we can start with the demonstration. So here we have the YED environment. I've already created a new graph. It's this unnamed 0. What we're going to do is to first create our different physical targets. So we're going to create a desktop PC and a compact RIO target. To do that, I'm going to use a group node over here. Just drag that down like you would in LabVIEW from a palette. Click on it and expand it so it's got a good size on it. And then I'll name it by double-clicking here. And we'll just call this desktop PC. And let's do the same to get the compact RIO target as well. If you notice as I'm dragging, we get some alignment bars. These are pretty handy when trying to keep your diagram nice and neat. They'll tell you when you've aligned it properly, like that. So we'll call this my NI compact RIO. There we are. And of course, within each of these, we've got our HMI VI. We'll also have our RT target VI and an FPGA VI. Within those are going to be a set of processes or loops that we're going to implement. So let's get a second level group node. Drag this in to desktop PC. If you notice, I get a nice alignment showing me that I'm at the center. I'll just keep it vertically centered for now. And we've also got auto grow available on the node. Double click here. This will be my HMI VI. And within here, I'm going to drag not a group node, but just a shape to represent my process. So I'm going to drop this here. F2 will also get you to where you can type a name. And I'll just call this my UI event handler. And main thing resizes, we do have to adjust this piece, but not that hard. And from there, I'll just take this, copy it, paste another one in so I don't have to resize it. And we'll call this one our command sender, because what I want this HMI to do is when a user presses a button, I want it to send a command over to the compact RIO. And let me copy and paste this one more time. And again, you see some nice auto grow features here, as well as that alignment. I like it. Again, F2 to rename, and I'll just call this my UI updater, because I assume I'm going to get some information back from the compact RIO, and I want that to happen here. So now we've got a pretty nice hierarchical view of what we have within the PC. Let's do the same on the compact RIO side. Make it nice and neat. Get a second level group node for my RT VI. And again, if you grab this guy and move him around, you'll get some nice alignment, so now he's nice and straight. This will be my RT VI. Make it a little bit bigger as well. And start dropping in some processes. So we're going to have some tag communication. If you remember from a previous lesson, the different types of communication that we have, tag, stream, or command. Tag might be, for example, the current CPU usage. It might be the current state the system is in, just the latest value. And that's what I'm going to want to show on the UI updater. So I'm going to align this nicely with the UI update. And if I click here and drag over here, that will create an arrow between them, like this. And if you notice the highlighting around that node to let me know that's where it's dropping. Let go. And now I've got a nice linkage between these two that handles movement for me. Let's move it back so it looks nice. And in this case, I might want it to be a two-way communication. So I would click on the arrow, right-click, go to Properties, and for the source arrow, if you notice, this one is just a line, no arrow. I'll make it an arrow. Hit OK. And now I've got a nice two-directional link. You could also just click on it and make the change here in the Properties view. Let's do some more of these. So I'm going to create some control process here. So I'll just call this control because I'm feeling very creative today. And get some nice alignment going here as well. Let me copy and paste this so I can do it a little bit faster. And align it with the command sender because this is going to be the command parser. And as you might guess, a command sender is going to send a command this way. So we'll click here, drag to the right, and now we have a link between command sender and command parser. I'm also going to want to have a link between the UI event handler to the command sender. I press a button, I want the command to go out. So I'll click here and drag down. So you can see pretty quickly how this is going to give us a very fast and easy to understand view of what the system is doing and what the different linkages are. Let me shrink this a little bit so I have some more room, and I'll add in my FPGA target as well. So align it nice to the top there. Get some auto grow going on this side, and I decided I want some more room, so I'm going to close these out. And now I've got a little bit more space. So let me rename this FPGA VI, and I'll get a node in there. That's my hardware communication. And the control piece of this is going to have a two-way link with my FPGA I/O. So draw my arrow, select that arrow, and over here, make it so that the source is an arrow instead of this line. And voila! We now have a pretty quickly made, but very readable, very clean, very functional diagram of what the communication in the system will be. I can shrink this a little bit and make it look all nice and aligned and pretty. Something else that you may notice as you build through these applications and make bigger and bigger diagrams is that maybe this shows too much detail. Maybe this is too big. If you notice, this button will allow us to shrink it down. So now I could just have a short name here, just call it CRIO instead of NI Compact RIO, and we retain those linkages as well. And if I move this around, you see some of the links get a little bit squirrely. That's alright. But you can still move things around, and of course my favorite, the undo button, to get us this retention of where we were. It's not perfect software, but it does have one very nice redeeming advantage. It's free. So if you're looking for a good diagram tool to get you started with your applications, YED's a good way to go. As you get more developed in your software development processes, I do recommend giving UML editors a look, as they'll let you create other types of diagrams as well. I haven't seen many, though, that will give you as much power as fast as this tool will give you, and particularly none that give you that at the same price. So that's the YED program, and it's also the program that we use to create all the system diagrams that we're going to see in the upcoming slides. Now you can describe how to create your own data communication diagram using an example diagramming application, in our case YED. In the next lesson, we'll describe the diagram of a typical real-time system. In the previous section, we described how to create a data communication diagram using an example diagramming application. At the end of this module, you'll be able to describe the diagram of a typical real-time system. Here we have a sample communication diagram for a typical real-time system. If you remember the last lesson where we looked at the YED environment, this might look surprisingly familiar to you. So almost all control and monitoring systems are going to start off with this basic architecture and be some variant of this. On the left side, you have your desktop PC target, which has some client VI. Typically, we're going to have processes there for updating the UI based on information received from the RT system, some UI event handler to handle the user clicking some buttons, and a command sender to let the RT system know what the user is directing them to do. Over on the right side, we have the Compact RIO target consisting of the RT VI and the FPGA VI. Have some form of tag-based communication over to the UI for latest value updates, usually system status, things like that. Some form of command parser to accept commands that were sent in from the desktop PC, and then a software control piece that will do the actual work of the system. There might be a PID loop here, there might be some level checking, there could be a recipe engine here, something that will actually execute the code that you built the system to handle. Typically, that section of code will be communicating down to the FPGA to handle the low-level hardware I/O control. Let's take a little bit closer look on the next slide. And here we have the basic HMI diagram. Again, 3 basic processes that you're going to find in almost every real-time application. Some form of updater that updates on a periodic basis. So not a command, not a stream, but a periodic update which will be done via tag communication. Some UI event handler that will use an event structure to generate UI events. So as we talked about in the previous lessons, this is going to be obviously a periodic process. When the user presses something, the UI will update. The UI event handler will be an event-based process when the user clicks something. The command sender is going to process whatever the user directed us to do and will communicate messages over to the real-time system. Typically the command sender is going to be only sending commands over to the RT system, but some variants of an RT application could have commands coming back the other way as well, from RT to the PC. Over on the Compact RIO target, we've got the RT target VI, periodic communication via tags in the tag communication loop up top, high-level control operations in the software control process, and handling messages to or possibly from the host, depending on which variant we're using here. And of course, the FPGA VI is what's going to manage our hardware I/O and control, and is what's going to be handling the deterministic control algorithms within the system. Anything that needs sub-millisecond resolution, you probably want to put that down on the FPGA VI. If it needs to happen within 100 nanoseconds, an RT target is not going to be the best place to put that. The FPGA is much better suited for that type of work. our T target is going to be where we put any operations that are best suited for floating point operations, anything that touches the network, file I/O, or central data stores that are managed on the RT side. Now you can describe the diagram of a typical real-time system. And coming up next, we're going to describe various real-time system diagrams that are a variant of that typical real-time system.